Welcome to the next class of data communication networks. So in our previous class, we were talking about error detection and the structure of encoder and decoder in the error detection technique. So let us try to have a quick recollection of those concepts. So we discussed here the total message to be transmitted is divided into smaller units called blocks, and the data is referred as data word, and to that data word, which is of k bit length, we are going to add r bits of redundancy bits and transmitting the k plus r bits, which is equal to n, which is the length of the code word. So code word is a combination of data bits and redundancy bits. Now once the data is transmitted through the channel in form of code words, it is received at the receiver. Now at the receiver, we have the checker performance. In case of error detection, the checker verifies if the data received is correct or not. If it is no, then that data will be discarded. If it is yes, the data will be forwarded for the further proceeding, where we are removing the redundancy bits and we are trying to extract the data. So in error detection, we'll only try to find out if the error is present or not. If there is no error, we'll extract the data. If there is an error, we will discard the data. Now coming to the next process called error correction, whenever an error has been detected by the checker circuit. So till this point, the process is same. That message divided into smaller units called data words, redundant bits are added to the data words and converted as a code word, transmitted from the sender to the receiver, at the receiver end forwarded to the checker circuit. At the checker circuit, if there is no error, it will be forwarded to the next layers. We'll separate the redundancy bits and we'll extract the data. But in case if an error is detected at the checker circuit, here we have two types of error correction process. If the receiver itself would like to correct the error present in the code word received, that process will be called as forward error correction. Let me mention you. If you are trying to verify the correction at receiver itself, we are calling it as forward error correction. Forward error correction is a process where you are trying to rectify the mistake at the receiver itself. But in case if the receiver is not intending to do that correction, so what it does is it will be asking the sender to retransmit the same code word. So instead of receiver correcting the error, if it is asking the sender to retransmit, that is called the reverse transmission. Okay, and that is also referred as retransmission. So we have two types of error correction. One is forward error correction, where the receiver itself will try to find the error and try to correct the data. If not, it will ask the transmitter to resend the same code. Okay, so this is the difference between error detection and error correction. There, if the checker is identifying the error, we are discarding the packet. But in the error correction, we are either correcting the error by ourselves or asking the sender to retransmit the same data. Got this one? Right. Right. The first error detection technique which we are going to discuss is called as Hamming distance. In Hamming distance, we have the next concept called minimum Hamming distance. But let us first try to understand what do we mean by Hamming distance and how it is associated with error detection and correction. Okay, now Hamming distance between two words is the number of differences between the corresponding bits. For instance, I would like to refer it with a simple example. If the first code word received is 1011 and second code word received is 1000, 0, 1. So what is the Hamming distance between these two code words? Now, if you look at this, the first bit of both code words is same. The next bit, second bit of both code words is same. The fourth bit of both code words is same, but only the third bit of the two code words are different. So the number of bits in which two successive code words are differ is referred as Hamming distance, and for this two set of data words the Hamming distance is 1. Okay, I hope this concept is clear. If you are referring two words, the number of bits in which those two words are different will be referred as Hamming distance. Now let us take some simple examples. Now we need to have a simple process to identify the Hamming distance, and we in the last class talked about an operation called modulo 2 addition or exclusive OR operation. So that can help us in determining the Hamming distance. For instance, we are take this particular example. The two data words we are considering are 000, 011. I want to find out the Hamming distance between the two bits. Now first let us put it on the slide. The first bit is the first data word is 000 and next data word is 011. Now in this two we could find this is same, they are different, and they are different. So the two data words differ in two positions. There is another way to calculate our Hamming distance. Now what we have to do is we have to do the exclusive OR operation of the corresponding bits. For instance, in this case, we have to do the exclusive OR operation. 0 exclusive OR. Let me recollect. In exclusive OR operation, if two bits are same, that is 0 and 0 and 1 and 1, the 0 exclusive OR 0 or 1 exclusive OR 1 is equal to 0, and if two bits are different, that is 0 exclusive OR 1 and 1 exclusive OR 0 is equal to 1. So using that rules here, 0 exclusive OR, we are trying to implement the exclusive OR addition of the two data words. Now 0 exclusive OR 0 is 0, 0 exclusive OR 1 is 1, 0 exclusive OR 1 is 1. So we have total two ones in the resulting exclusive or modulo 2 addition of the two data words. That is the reason why the Hamming distance here is referred as 2. So similarly, next problem. Here we have 10101 and 11110. Let's put it here 1 0 1 0 1, and next we have 1 1 1 1 and 0, and we are expected to calculate the modulo 2 addition or exclusive OR between these two data words. Now I want everyone to be able to answer to it. Now the same rule, two bits are same, the exclusive OR is 0. If two bits are different, the exclusive OR resultant is 1. So 1 exclusive OR 1 is 0, 0 exclusive OR 1 is 1, 1 exclusive OR 1 is 0, 0 exclusive OR 1 is 1, 1 exclusive OR 0 is 1. So totally you could find total number of ones in the resultant exclusive OR operation is 3. So hence the Hamming distance between the two code words 10101 and 11110 is 3. Now we have the other definition. Number of positions in which the bits are different. 1, 1, same. Let me first erase this. Right? Okay. These are same. 0 and 1 are different. So we'll put it as a cross mark. 1, 1, same. 0, 1, differ. And 1, 0, differ. So number of bits in which the two data words are different are 3. Hence the Hamming distance is 3. So this is, let us learn to understand here is that Hamming distance is one of the very important parameter to identify how many errors can be detected and how many errors can be corrected. So everyone make sure you understand Hamming distance. And first important thing here is in Hamming distance, whatever the number we have to represent in binary form in form of ones and zeros. Clear? Right. Right. Let's go for the next one. Minimum Hamming distance. Now we were talking so far about identifying the Hamming distance between two data words or two code words. But suppose I got different sets, code word 1, code word 2, code word 3, code word 4, and I will have different Hamming distance between C1, C2, that is code word C1, C2, different Hamming distance for between C2, C3, C3, C4, C1, C3, C3, C1, C4, and so on. When I have different combinations of code words, how do I identify the minimum Hamming distance? So minimum Hamming distance is the smallest Hamming distance between all the possible pairs in the set of words. Just now we have said we can have combinations like, we have divided total data into 4 code words: C1, C2, C3, and C4. So the Hamming distance between C1, C2, C1, C3, C1, C4, then C2, C3, C2, C4, then C3, C4. So totally we have 6 combinations. Whichever the combination is providing us the minimum value, that will be referred as minimum Hamming distance. Now let us take a simple example to understand what do you mean by minimum Hamming distance. Right. So a simple example, we have the combination like data is 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. Let me put the 4 code words which we have are 0, 0, 0, 0, 1, 1. Then we have 1, 0, 1, 1, 1, 0. So totally there are 4 pairs and we are trying to determine the minimum Hamming distance. Now coming to the first two, one is 0, 0, 0 and 0, 1, 1. You could easily identify 2-bit positions are different, so there the minimum the Hamming distance is 2. The next pair 0, 0, 0 and 1, 0, 1, the number of bits in which they are different. 0, 1 is different, 0, 0 same, 0, 1 is different. So again the Hamming distance is 2. The next combination 0, 0, 0 and 1, 1, 0, again they are different 2-bit positions. Next 0, 1, 1, 1, 0, 1, we have the different set 2-bit positions: 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0. Again it is 2. and last case 101 and 110, again it is 2. So all the different combinations of code word, the distance, the Hamming distance is 2. So the minimum Hamming distance is 2 in this particular example. Now we'll take another example where the Hamming distance values will be different. Before we go for the example, let me erase this what we have written. Right. Here you could find data words 0, 0, 0, 1, 1, 0 and 1, 1 represented with 4 different code words. 0, 0 is indicated as 0, 0, 0, 0, 0. Data word 0, 1 means data word length k equal to 2, redundancy bit r equal to 3 and n equal to 2 plus 3 equal to 5. So we have different code words like 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1 and 1, 1, 1, 1, 0. We need to find out Hamming distance between all the possible code words. First we'll start with 0, 0, 0, 0, 0, 0, 1, 0, 1, 1. Now check out here, first bits are 0, 0, second bit is 0 and 1, so it is 1 difference. Third bit is 0, 0, again they are same. Fourth bit is 0 and 1, fifth bit is 0 and 1. So totally out of 5 bit positions, in 3 bit positions they are having different values. So the Hamming distance between 0, 0, 0, 0, 0 and 0, 1, 0, 1, 1 is 3. Similarly 0, 0, 0, 0, 0 and 1, 0, 1, 0, 1, you have at 3 different positions, first, third and fifth. It is different from next code. Third case also you have, here you have 0, 0, 0, 0, 0, 1, 1, 1, 1, 0. So totally 4 bits are different. So the Hamming distance in this combination is 4. For remaining combinations you can find 0, 1, 0, 1, 1, 1, 0, 1, 0, 1. 0, 1 is different, 1, 0 is different, 0, 1 is different, 1, 0 is different, and last bit is 1, 1 which is same. So out of 5, 4 bit positions are different, so the Hamming distance is 4. Next combination we have the Hamming distance equal to 3, and last combination we have the Hamming distance equal to 3. So totally with 4 code words, 6 combinations we verified, and out of 6, 4 are having a Hamming distance of 3 and 2 are having a Hamming distance of 4. So which is least among this all possible values? So 3 and 4, the least value is 3. So the minimum Hamming distance in this scenario is 3. So we just talked about what do you mean by error correction. Then we started discussing about one of the error correction technique called uh, Hamming distance and minimum Hamming distance. So Hamming distance have a relation with the error detection and error correction. We'll just go through it next. Right. Now what is the significance of learning minimum Hamming distance and Hamming distance is, suppose if I want to correct S or I want to detect S number of errors, the minimum Hamming distance in a block code I require is S plus 1. Means if I want to detect one error, then I need to have a minimum Hamming distance of 2. If I want to detect 2 errors, I need a minimum Hamming distance of 3. So that is what the Hamming distance, minimum Hamming distance is related with the number of errors that can be detected. Similarly, there is a relation between minimum Hamming distance and error correction. What is that? If S number of bits are to be corrected, the minimum Hamming distance required is d minimum equal to 2s plus 1. Means if I want to correct one bit of error, if s equal to 1, the minimum Hamming distance required is 2 into 1 plus 1 equal to 3. So for one bit of error detection, minimum Hamming distance required is 2. For one bit of error correction, the minimum Hamming distance required within the code words is 3. So this is how minimum Hamming distance is related with error detection and error I hope things are clear with relation between minimum Hamming distance, error detection, and error correction. So coming to the error detection techniques, first we need to understand a concept called linear block codes. Initially we have started our discussion with block coding, where we are trying to divide the total message into smaller units called data words, which is referred as blocks, and then to that data words in the block we are adding redundancy bits to convert it into code words, and that concept was referred as block coding. Now what do we mean by linear block codes? So almost all the block codes which we are using today are subset of linear block codes. A linear block code is a code in which the exclusive or addition of two valid code words create another valid code word. For instance, if I am trying to take two code words and I am trying to do the modulo 2 addition or exclusive OR operation of those two code words. So whatever the resultant that is being generated by those two code words modulo addition should generate me one more valid code word. And that kind of code words will be referred as linear block codes. So here what we are going to discuss is what is the minimum distance for the linear block codes and some of the linear block code techniques. I hope it is clear, simple. Dividing message into smaller units called data words and adding redundancy or code words, and the process is called block coding. And if two code words are implemented in modulo 2 addition, and if it results in another valid code word, then that will be referred as linear block code. Okay. So one of the simple examples of linear block code is parity check method. And basically a simple parity check method is an one bit error detection technique. So n bit one bit error detection technique. So s equal to 1. So definitely the minimum distance d minimum is s plus 1, which is equal to 1 plus 1 equal to 2. So for a parity check code, the minimum Hamming distance is 2. The relation between code word length n and data word length k is n equal to k plus 1, means we are in simple parity we are going to add one redundancy bit. I hope this is clear. So parity check method is one bit error detection technique with a minimum Hamming distance of d minimum equal to 2, and the relation between the code word length n and data word length k is n equal to k plus 1. So let us take a simple scenario of simple parity check of C of 5 comma 4. So here 5 is indicating actually the length of code word, and 4 is indicating length of data word. So 5 is nothing but n, and k is nothing but 4. Okay, now just look at the table which we have been projected. So here we are believing two types of parity check methods. The first one is even parity check. So let me put you on. The first type of parity check is called even parity check. Now what do you mean by even parity check? If your code word, so in everyone make sure you remember the definition. In even parity, the total number of ones in the code word, including the data word and redundancy bits, should be even. Total number of ones in the code word should be even. At the same time, if you are expecting an odd parity, total number of ones including the redundancy bit will should be odd. So if number of ones are odd, you will call it as odd parity. If total number of ones including the redundancy bits is even, we are going to refer it as even parity. Now let us start taking a simple table to understand this difference. So first we have a data word width of length k equal to 4. We have just learned in the previous slide, for simple parity check, the redundancy bits are equal to 1 and that will be added at the any corner of the data. Now total, suppose we are taking in this example the case as even parity. So total number of ones including the redundancy bit should be even. So or we have all zeros. The total number of ones is 0. So redundancy bit is r, and the value of r should be such a way that, let me keep it as r. So the value of r should be such that the total number of ones including data and redundancy bit should be even. So for this scenario, so 0 0 0 0, already number of ones is 0, which is even, so the r should be 0. But in the next case, the data word is 0 0 0 1, so the number of ones here are odd. To make that total number of ones including redundancy bit as even, we have to set r equal to 1. Now the total number of ones is 2, which is even. Third, 0 0 1 0, number of ones are odd, so the redundancy bit should become 1, so that total ones are even. 0 0 1 1, here the total number of ones itself is already 2, which is even, so the r bit should be 0. So what is required here is, depending on the type of parity required, the value of r bit should be set such that the total code word is following that particular required parity. So let me have a fast quick understanding of all these examples which we have. So 0 1 0 0, odd number of ones, so the redundant bit is 1. 0 1 0 1 is 2, which is even, so the redundant bit is 0. 0 1 1 0, total ones are 2, which is even, so the redundant bit is 0. 0 1 1 1, 3 ones, which is odd, to make it even, r becomes 1. Similar, 1 0 0 0, total ones are 1, which is odd, to make it even, 1 0 0 1, even, so we have r equal to 0. 1 0 1 0, even, so r equal to 0. 1 0 1 1, odd, r equal to 1. 1 1 0 0, even, so we put r equal to 0. 1 1 0 1, odd, so r equal to 1. 1 1 1 0, odd, so we are going to place r equal to 1. Last one, all 4 bits of data would are 1, which is even, so we will have redundancy bit as 0. So this is one of the first and simplest error detection technique called simple parity check, where total number of ones including data word and redundancy bit should match the required parity. If even parity is followed, the total number of ones should be even, and if odd parity is followed, total number of ones including data and redundancy should be odd. Got it? I hope things are clear here. We'll move to the next one. So how exactly we are implementing this particular simple parity check? First, we have taken simple case of 0 0 0 0. So that is our data word. Now I need to find out the redundant bit so that I can create my code word. So what is the logic here? Find out total number of ones, then depending on the parity, I can set the value of a redundancy bit, and then I can generate the code. Got it? So total number of ones are odd and we require even parity. So R becomes 1. Total number of ones are even and I require even parity. So the R becomes 0. So it is a simple parity check code. Is we are trying to consider a data word, determine the redundancy bit, and then transmit the data word along with redundancy bit, which is together called as code word. Now at the receiver, we are trying to receive the code word which we have received, and now this is forwarded to a check device, which is called checker. Here we are trying to calculate a value called syndrome. So what is syndrome is nothing but the exclusive OR sum of all the bits in the code word. Remember, if you are requiring for odd parity, the value of the syndrome should be 1, and if you are looking for even parity, the value of syndrome should be 0. So what it is and why, let me just explain you. If I have 0, 1, 1, 0, and what is syndrome value? It is nothing but exclusive or sum of all the bits. 0 exclusive or 1 is 1, 1 exclusive or 1, 1 exclusive or 1 is 0, and then 0 exclusive or 0 is 0. So finally we have 0 exclusive or 0 is equal to 0. Now if total number of ones are even, for even the syndrome should be 0, and for even numbers the syndrome should be 0, and for odd parities the syndrome value should be 1. So here we are trying to calculate the syndrome, and if the syndrome, if you are following even parity, if it is equal to 0, then the decision logic circuit indicates the received data bit code word is correct. We'll try to remove the redundant bit and we'll accept the remaining bits as data word. But if we are following even parity and if we get syndrome value as 1, when do we get an syndrome value 1 in even parity? If one of the bits that is received got changed. Before we transmit itself, we are ensuring the total ones including the parity bit are even. But at the reception, if one of the bit got corrupted, a total number of ones become 1, odd, and whenever you have total number of ones as odd, the syndrome value will be, so for odd number of ones, the syndrome value is 1. But what is required here? Even parity. So the syndrome value should be 0. So whenever a 1 bit got affected, the syndrome becomes 1 and the decision logic will reject the data, and then we have to discard the data. Remember, simple parity check is only error detection or technique. If it is correct, it will be removing the redundancy bits and try to extract the data word. If it is getting an error, that will be discarded. So here we have right. So we'll take a simple example of a data word 1011 and we are implementing even parity. So as per the rule of even parity, the total number of ones including the data word bits and redundant bits should be even. So here total number of ones in the data word is 3, which is odd, but our required scenario is even. So what should be the value of redundant bit to be set? So the R value should be 1. So the code word which is sent from the sender to the receiver end is 10111. Now here we'll have different types of scenarios which can be observed. If I am transmitting 10111, unfortunately there no error occurred during the transmission and the received code word is 1011. So whatever has been transmitted is as it is received. So when say received code word is received, you are going to try to determine the value of syndrome, which is generated by exclusive OR of individual bits. So one exclusive OR 0 is 1, then one exclusive OR 1 is 0, 0 exclusive OR 1 is 1, and finally one exclusive OR 1 is 0. So here syndrome is 0, and we remember that in even parity, if the syndrome value is 0, then we assume no error has been generated, and we'll try to remove the redundant bit and try to extract the data word, so which is considered as 101. So this is the first case where what we transmitted is received as it is at the receiver, and we have tried to extract the data word. Now the case 2 is what you transmitted was 10111, and there is one single bit error changes. And what is received actually at the code word? So instead of 10111, we have received the data as 10011. So there is one bit change that has been happened between the first case, which is 10111, and in the case 2, which is received as 10011. So when you are having one bit of change, try to find out the syndrome value for the received code word. Now remember, what is syndrome? Exclusive OR of all the individual bits in the received code word. One exclusive OR 0 is 1, one exclusive OR 0 is 1, one exclusive OR 1 is 0, 0 exclusive OR 1 is 1. So here the syndrome value received of the code word is 1, but when you are following even parity, the expected syndrome value is 0. Since there is one bit of error generated, the syndrome has changed from 0 to 1. So one bit of error is detected, and we are going to discard the data. Now third case, the change may not be only in the data word which you find, but even the bit that can be changed is, here we find a change in the data word 1011, which is our data word changed as 101101. This next case, 1011 data word has transmitted as it is, but the redundant bit which we have taken was 1 at the receiver, it has changed to 0. Now what happens here? Again try to determine the syndrome value. The total number of ones are odd. So whenever the number of ones are odd, the syndrome becomes 1. But even parity, the syndrome required is 0. So whenever the syndrome gets affected, that particular data will be discarded. Right? This is scenario 3. Scenario 1, there no error occurs. Scenario 2, out of 4 data word bits, 1 bit got affected. Again it is discarded. In the third case, the data words are same, only the redundant bit got affected. Again the data is discarded. Next, an error change occurs in both redundant bit as well as one of the 4 data bits. So instead of what we have transmitted, the received code word was 00110. Okay, so what happened here? This is the received code word. One of the data bit got changed. At the same time, the syndrome value also changed from 1 to 0. Now when you try to calculate syndrome, when 2 bits have changed from 0 to 1s. Now what is the problem here? The syndrome of even number of ones is 0. So if you calculate the syndrome, it is 0, and for even parity the syndrome is 0, and we feel that data is correct. And with this wrong perception, what happens? We try to remove the redundant bit and try to extract the data word. What the data transmitted was 10110, but what we received was 00110. Though we have 2 bits of error, but still we are considering it as a correct data, and we are extracting the data. The problem is the parity check does not detect more than one bit of error. Okay. Again, if there are 3 bits of errors, so 3 data bits got affected, what happens now? Let me take. So again, if when number of ones are odd, the syndrome is 1. So whenever syndrome is 1 in even parity, that data will be discarded. So what we could observe here is our parity check technique here can be identifying the odd number of errors generated, but not for the even number of bits of errors generated. This is what we need to observe in 5 different cases. No error, only one bit of error in the data word, one bit of error in the redundant bit, then one bit of error in data word and one bit error in syndrome, redundant bit, and there more than 2 bits, that is 3 bits of data word got affected. I hope people are able to understand what we have been understanding here. So a simple parity check code can detect an odd number of errors. Now last thing before we close the session is, here we were trying to calculate the parity bit only in one dimension. We are considering horizontally trying to determine total number of ones and depending on the type of parity. For instance, this is my data word and I need to generate a code word and I am following even parity. So here total number of ones is 5, which are odd. So I require even parity, so the redundant bit is set to be 1. 10111101. Total number of ones are 5. I require even, so again R equal. Next 011001. 4 ones, so redundant bit 0. 010101. Number of ones are 3, so it's odd, so again I'll set redundant bit equal to 1. This is simple parity. But in this next case, what we try to do is we try to determine the parity in 2 dimensions, that is both horizontally and vertically. So I'm going to represent all the data words which I have from the original message in this form, and then I'll try to calculate parity bit value not only in horizontal side, but also I try to calculate the parity bit value in vertical side. So here we have 4 bits. Now total number of ones are 2, which is even, so I have redundant bit as 0. Total number of ones are 3, so redundant bit is 1. 2, so redundant bit is 0. 3, again it is odd, so I have redundant bit 1. So I calculate the redundant bits horizontally and vertically. Okay, this is called two-dimensional parity check method. So here also there is a scenario like there is one bit of error generated. Now what happens if one bit of error got generated is two parity bits are getting affected. Suppose in the previous data which you have shown, only one bit got affected. Now this effect will be impacting on the value of parity bit at this position, because earlier it is 0, but now it will change it from 0 to 1. So total number of ones become 5, which is odd. So the parity bit changes to 1. Similarly here, earlier it was 0, 0, 1, 0. So number of ones were odd. So we have taken parity bit as 1, but now it is got affected as 1. So total ones have become 2. So the parity bit value becomes 0. If one bit of error is generated, it is going to affect two places in two-dimensional parity. If two error effects, you will find here the impact of two errors getting, so two generated affecting the different parity effects. Important things that we would like to understand about two-dimensional parity check code is, in two-dimensional parity check coding, for each row and column, one parity bit is generated. That is what we discussed. The whole table will be sent to the receiver where syndrome values. Earlier we were trying to calculate syndrome value only row wise, but here we are going to calculate the syndrome value row wise as well as column wise. And that is the advantage we have here for two-dimensional parity check code is Total number of errors that can be detected here is 3 errors. So your two-dimensional parity check can detect 3 errors. So generally the Hamming distance required when you can detect up to 3 errors is d minimum equal to 3 plus 1, which is equal to 4. So we'll hold our discussion here. We'll try to discuss the remaining techniques in our next class. So let us quickly try to give you a glimpse of what we have discussed in today's class. We started what do you mean by error correction and how the encoder and decoder exists for the error correction. Then we started talking about different error detection techniques. First, for that, we try to understand what do you mean by Hamming distance, which is nothing but number of bit positions in which two code words differ. Then we try to understand what is minimum Hamming distance, the relation between Hamming distance and minimum Hamming distance with error correction and error detection. For error detection, d minimum equal to s plus 1, where s is number of bits of error detected. For error correction, d minimum is 2s plus 1. Then we started about first error detection technique called simple parity check, where we are trying to divide the data into data words and we are adding one redundant bit depending on the type of parity. And at the receiver, we are trying to calculate a value called syndrome, which is the modulo 2 addition of all the bits received at the core receiver. And depending on the parity type and the syndrome value, we are either discarding the packet or we are extracting the data word. The next level of simple parity check is called as two-dimensional, where you are trying to calculate the parity bits not only horizontal wise but also vertical side. With this, what happens is we can detect up to 3 errors and syndrome value which we are calculating only in one dimension, we will be able to calculate this time in 2 dimensions. We will discuss the remaining topics in the next class. Thank you.